When we look at individual reactions, we want to avoid different phases trying to interact with each other. Okay? And as we'll talk about maybe a little bit later today, if not Thursday, when we look at the speed of a reaction, and there's a couple things we're concerned about when we look at a reaction. Number one, is it likely to occur? Right? Well, if it's likely to occur, then that's probably one worth trying to do. If you started a reaction that had no chance of ever occurring, does it make sense to even start that? No. Okay, so we want to look at a likelihood of it potentially happening, and that's going to be referenced as equilibrium. We'll look at that probably later today. The other aspect we want to look at is how fast it occurs. Okay? We all combust. Okay? Just by respiring, breathing, we are in a combustion process. Okay? And an interesting extra term that we can add to that when we look at the likelihood of a reaction occurring is that if that reaction likely occurs, we refer to it as spontaneous, which is kind of fun because if we now combine those two concepts, what are we doing? We are spontaneously combusting right now. Okay. When we move to chemistry, spontaneous just means does it happen? It says nothing about the speed. So when we think spontaneous, we think, oh, speed, it's happening fast. It's not necessarily the case. Okay. So we have the likelihood of the reaction occurring and how fast does it occur? Does it happen really, really quickly? Okay. Or does it happen over a long period of time? Thankfully, when we look at ourselves spontaneously combusting, the rate or the speed of that reaction is a very long time, or it's a very slow reaction. Okay. How is that important for us? Well, if we're looking at any general reaction that we're going to put two things together and we want them to react with each other, we want to make sure that they can react as fast as possible. The longer it takes to react, the longer we're sitting in lab, the longer we're sitting in lecture, it gets boring. Okay? So we want to speed it up as fast as possible. One of the ways we do that is ensure that all of our reactants are in the exact same phase. Okay? If they're all in the same phase, they all mix evenly, we get the best possible chances of those particles colliding and forming products. Okay? The easiest phase for us to work with, or the most efficient one, I guess, in that case, is really going to be the gaseous phase. Okay? That's because every particle is completely free from every other particle. As we move to liquids and solids, what ends up happening is that we're now trapping, we're putting a barrier on one side of our molecule because it's covered with the rest of like molecules. So we want to minimize that barrier as much as possible, and that's where the gas phase comes in handy. The issue with the gas phase is that if we take our chemicals and put them into the gas phase, we run into this issue of, well, how do we trap them in a particular area so that that gas phase reaction is only happening in the test tube and not, say, in the air we breathe. Okay? That's kind of a problem. We could close the container, but then if we do a reaction that forms more molecules, we have kaboom, it's an interesting way to phrase it. We have a bomb. We have a closed container with rapidly expanding gas. That's a problem. Okay? So gas phase reactions are not the easiest to work with. Well, we just eliminated solids and liquids from our list. We now have a problem. We've eliminated all possible standard states of phase, except aqueous. If we take our compounds and dissolve them in water, what is necessarily happening is that each of those particles now moves away from each other, and they are now surrounded by water. What we have done by putting things into the aqueous phase is effectively put things into a gas. Everything has now been freed away from everything else. We are in a pseudo-gas phase system. We have a way that we can now control our gas, if you will, because it's trapped within the liquid of water, and it can allow for a smoother reaction. That's why when we do all of our reactions, we run them in the aqueous phase, because it's as close as we can get to the gas phase without going all crazy and running into safety issues. The issue with putting it into water is that now when we do this reaction, is it just aluminum bromide and just silver nitrate that's present? No. I also have water present. Okay, well, in and of itself, that's not a big deal because it's not involved in the reaction. But how do I measure out how much aluminum bromide I've got? How do we typically measure something out? We could measure the volume. Okay, aluminum bromide is a solid. Well, we dissolved it in water, so now I can measure the volume. So I can measure the volume of that solution. Does that tell me how much aluminum bromide I have? No, that tells me the volume of my aluminum bromide and water. Okay, so that doesn't get me the aluminum bromide by itself. Before we add it to water, we could measure the mass of the aluminum bromide and then dissolve it in water. Okay. Perfectly valid, and in a real world situation, you probably would end up going through and doing that process. Okay. The issue with that is that it slows things down. So when you go into lab, you didn't measure out a solid each and every single time. In most cases, you measured out a solution, and you mixed two solutions. We still need to be able to figure out or come up with some way to get an exact amount of the aluminum bromide used. Because if I know the exact amount of the aluminum bromide used, I can use the balanced equation to convert to our products. Okay? So we've got volume, but that includes the water. We've got mass. Before we start the experiment, that's clean, but we don't have that. So if we do it during the experiment, that also includes water. So I need some way to measure or tabulate the concentration. How much aluminum bromide is in the water solution?
Don't we usually just heat it to dry it out?
So we can heat and remove all of that water. So we could start with the solution. Okay, we walk in the lab, they give you a solution of aluminum bromide. To figure out its concentration, you are absolutely right. We could boil off all the water. You boil off all the water, you now know the mass of aluminum bromide. The whole point was to be able to predict what our products were, though. So now what do? You add all the water right back in and do your reaction next and boil off all the water, okay, to get your final product. It would work. That's a lot of extra steps.
Do you take another compound, take the measurement of that, then cause it to bond to that one?
We can do what's known as a titration to figure out an exact concentration. But we could just walk in and say, whoever put the solid in the water, tell me how much you put in. Okay. I now have a concentration. Okay. So what we're doing is looking at a conversion factor that allows me to relate the amount of a substance to the volume of that substance. Okay. All we're looking at is a concentration. Okay. What units we use on concentration are kind of arbitrary. Okay. You've probably seen percents. In fact, in lab, you looked at percents, sort of looked at percents. We could say it is the percent of grams of aluminum bromide in 100 grams of solution. Okay, that would be a percent by mass. That would work for us. We could make it 100 milliliters. Okay. We could do liters. We can do any arbitrary unit system we want to use. Okay. And ultimately it's going to come down to what do we want to use. Well, we're trying to determine how much product is made. How do I convert from reactants to products? What from the balanced equation? What units from the balanced equation? What ratio? Nope. Moles. A mole ratio comes from the balanced equation. If I give you 1 mole of aluminum bromide, how many moles of silver bromide are made? 3. If I give you 1 liter of aluminum bromide, who knows? What's the concentration of that solution? I'm not giving you 1 liter of aluminum bromide. I'm giving you 1 liter of an aluminum bromide solution that has water in it. Well, that water is taking up that volume as well. Okay? So we're going to need to eventually get into moles. So what's going to be the best concentration unit for us to work with? Probably one that starts with moles in it, so we don't have to worry about doing some extra conversions to get into moles. So when we're in a chemistry lab, or in most labs, we end up working with a molar solution. It's the moles of our substance per the volume of our substance. Okay? We refer to that as molarity. Why? I don't know. Okay? Because it says mole in it. And you will also often see it referred to as capital M, okay, which is kind of obnoxious and kind of useful at the same time. Okay? If I wanted to say the molarity of the aluminum bromide, I could go through and say, well, it's 3 molarity. It's an awful lot of letters, so we can cut that down to 3M, capital M. Why capital and not lowercase? Lowercase is meters, so we want to use a capital M to distinguish from that. Okay? We don't work with capital M units, though. So anytime you see a capital M unit, you should immediately change that unit to become moles per liter. You notice I went with the slash right away. Slash is always useless, so we should convert that out to 3 moles in 1 liter. Why 1? Okay, so we could try and run just straight from our definition. It's by definition moles per liter, which means moles per 1 liter. But why is it 1? If it is anything else, the 3 is not really a 3. Okay, so by definition, it is moles per 1 liter. That is our whole point. Okay? This now allows us to convert or measure a volume of our solution, convert that into moles of our particular compound in that solution. Once we know the moles of that compound, I can then convert across the moles of product. It is a conversion factor like any other conversion factor we've worked with this semester. Okay? So I believe we did this example. Should we walk through it again real quickly before we make you do the next one? Okay. I know, Tuesday was a while ago. Molarity of a solution. So we're looking for the capital M. To solve for the capital M, I know that is moles per liter. Okay. So to solve for it, I need to know how many moles in how many liters. Okay. I have a solution that contains 24.0 grams of sodium hydroxide in 0.1 liters of solution. Okay. So we're going to solve this a couple ways. First way we'll solve it is we'll break it into the 2 pieces. If I can figure out what the X moles are and the Y liters are, I can then move to that last step and do the division. How do we figure out the X moles? So it is X moles of what? Do I know anything about the sodium hydroxide to start with? I know I start with 24.0 grams of sodium hydroxide. I'm trying to get to moles of sodium hydroxide. Are those units the same? Nope. So I need a conversion factor. Grams to moles. Where do I find the conversion factor of grams to moles? By using the periodic table, I can determine the molar mass for sodium hydroxide, and I can drop that number in front of grams. So the molar mass for sodium hydroxide, sodium was what, 23? 23. Oxygen 16. Hydrogen is 1. And I get a molar mass equal to 40 grams per mole. The 40 shows up where? In front of grams, which is on the bottom. Okay. If I go through and do that calculation, what do I end up with? The moles of sodium hydroxide. I've got the value that needs to show up in my numerator now. Next part. I need the liters of my solution. Do I know anything about my solution? Oh, that's fascinating. Do I have to do any conversions? I'm given that number right away. Now what can I do to solve? We got 24 divided by 40 was what? I didn't actually calculate it. 9? I was like, I don't think that's right. 0.6. So I can say 0.6 moles of my NaOH, and I can divide that by my 0.100 liters, and I end up with my final answer of, is that 6 moles per liter? Very clearly I made a sort of, or not very clearly necessarily, but I definitely made a mistake in this answer. This answer is technically wrong. Hopefully it's wrong for the reason I'm thinking of and not for some other one. Fair enough. I didn't see that one. It needs to be molars of NaOH. There's another reason. Yeah, where was it? Sig figs. We'd have to watch out for the sig figs officially. We need 3 sig figs coming from our work. Okay. On a test, you likely would not be tested on the sig figs. And the answer, how do you know you're being tested on sig figs? If we looked at some other answer choices here, let's say that was answer choice A, what would answer choice B be? About 6 moles per liter. Answer choice C, 6.0 moles per liter. 5.99 moles per liter. Why not? And E. Okay. And yeah, we write it as goats just to be funny, but we could go through and say it's 0.2 moles per liter. Why would we not ask this question as a sig fig question?
Because the sig figs don't really change.
If those were my answer choices, what's the best answer? Okay. We got 16.2 as a possibility, but none of the other answer choices are even remotely close to it. More than likely, wrong. Next part, if we look at our answer choices, or our starting thing, how many sig figs do we have in our answer, or our starting numbers? 3, which then means wrong. Okay. And I could be looking at 5.99 versus 6.00. I've eliminated, with no work, 3 out of 5 answers. Okay. It's a pretty dumb question to ask as sig figs. Okay. More than likely, it would be a straight-up calculation one, and you'd end up seeing variations of 0.6 of that 6, either dividing by 0.1, multiplying by 0.1, dividing by 40, multiplying by 40, all those fun things. Okay. Questions on that? Can this all be done in one step? Do we know anything about the moles or liters of solution, given any information in the question? We just solved it, so hopefully you know the answer to that. Do we know anything about, thank you, what do we know?
1
We know 24.0 grams, but that's not moles or liters. Do we know anything else?
0.1.
I know 0.1 liters of solution. Right? Well, my answer needs liters of solution where? On the bottom. So what could I immediately do? What goes on top? Okay, so there's an interesting dilemma here. We could go through and put in 24 grams. Okay, that is fair enough to go through and do. If you didn't want to put in 24 grams, there's one other answer you could put in. If you put in 0.6, where did you get 0.6 from? From a calculation we already went through and did. You could throw up and start doing a, throw up, that kind of came out wrong. You could start pointing at the periodic table, okay? But the periodic table has nothing to do with the liters of solution. Left the liters off. Does our liters of solution convert to anything? Or is it just liters of solution? Again, look at the number that's written there. Does it convert to anything? No. So what should show up on top? Your units cancel and you don't have liters of solution anymore. So you can't put liters of solution on top. What needs to go on top? 1. What are the units? No units. Because if you put in units, do you have liters of solution anymore? No. If you use any other number than 1, what happens to 0.1? It changes and it's no longer 0.1 liters. Okay. So it's trying to find our relationships and put in those individual values. Okay. Next part, I would need moles as a unit on top. Was a measurement of sodium hydroxide. Do I have a measurement of sodium hydroxide? Given to me. I'm given 24.0 grams of sodium hydroxide. What would show up underneath it? 1. Why? If I put in some form of unit, what happens to my units of grams of sodium hydroxide? It changes. That's not what I was given. I was given grams of sodium hydroxide. I cannot put a different unit there. Just a sec. What about any other number? If I put in any other number, do I have 24 grams anymore? No. It's now changed as well. Why include the 1s? This helps us to see numerator versus denominator. Yes, Mahala.
I really don't understand what you mean by like the unit position.
Okay. What is 0.1 a measurement of? What is liters of solution?
A unit, a measurement.
There it is. It's a unit. Okay. So if I put in any other unit on top of this, okay, let's say liters of solution. If I now look at that value, what happens if I calculate it? What would my unit be? What would it be? It cancels. If it cancels, do you have liters of solution anymore? No, you've changed the unit. The unit given to you in the question was 0.1 liters of solution. By putting any other unit on top, what have you done? You've changed the information given to you. You've removed that information. You can't do that.
So now it's 24 grams of that over 1 what? Just 1.
Same issue when we move to that next conversion. We were given 24.0 grams of sodium hydroxide. We've already written 24.0 grams of sodium hydroxide. If I put it over any other number than 1, what happens to the 24? It changes. Was it 24.0 or was it any other number? It's 24.0. What about the units? What if I put it over 1 with some unit? Say moles. Exactly right. The number I was given with the unit I was given was 24.0 grams. Okay? So what we're trying to do is take the information out of the question and put things down exactly as given. We're not creating new conversion factors in this relationship. We're just saying these are the things I'm given. If I went through and solved this, what would I get as an answer for units? I'd get grams per liter. Okay, I'd multiply everything in the numerator and I'd divide by everything in the denominator. And I'd end up with units of grams per liter. Is that what I want for an answer? No. So now I need to include a conversion factor. That conversion factor needs to affect what? Where do I get that conversion factor? Which you've said already.
We already know it by heart, right?
It's not a by heart one. Your relationship between mass and moles is always found on the periodic table. The relationship to atoms and moles is the one you've memorized, and that's 6.022 times 10 to the 23rd. Okay? So we just calculated that. We said it was 1 mole was 40.0 grams. We set up all our work. You'll notice that all the calculations we are doing in this single line are the exact same as the calculations we did across 3 lines in the previous setup. All we've done is combined them into one setup. Okay. Are there other variations? Sure. But what we are trying to do is ultimately say, how do we convert those units and get them to match the final answer? Why do we want our units to match the final answer? The question asked for those units. You should probably solve for it in a way that gets you those units. Okay? That's what was asked of you. Kind of make sense? Okay. So if we go through with our skeleton, what do we want as an answer? I disagree. Grams of potassium dichromate. Now it's a question of what do we do with all our other information. As one big hint, if you see that capital M, you should immediately convert that into something more useful. Moles per 1 liter, and it would be moles of potassium dichromate, which I've run out of space there, but that's what it says in that corner. Right. So what information do you want to start with? Okay, so there's a couple answers we can go with. Is we could start with 125 milliliters. How many people started with 125 milliliters? Like 4 people. Okay, so I'm going to split this into 2 lines, and then, or 2 methods, so that we can see how this works out. It's a little bit higher, right? CR207. So if you were one of those people that started with 125 milliliters, we'll stick with that. Okay. This is milliliters of, technically, solution. It's our potassium dichromate solution. Are milliliters of solution the same thing as grams of potassium dichromate? No. So what do we need? Conversion factor. Ideally, we would go milliliters to grams, which we don't have. So you said, okay, well, I know how to convert milliliters to liters. Okay, I can accept that. How do you convert milliliters to liters? The 1 liter is 1,000 milliliters is technically correct. There's a reason I'm not writing that down, and that's because that's not how we told you to deal with this. You should remember that milli means 10 to the negative 3. That unit shows up in front of your base unit, which is liters, and we'd have 1 milliliter underneath. So we're now in units of liters of solution. Is liters of solution the same thing as grams of potassium dichromate? No. Okay, so what needs to show up on the bottom in the next step?
Liters.
Liters of solution. Do I have anything that converts liters of solution to anything else?
Yes.
Yes. What is that?
The molarity.
The molarity. What numbers need to show up?
0.150.
Shows up where?
The moles.
In front of the moles. Good answer. And 1 shows up on the bottom. What unit do we now have?
Moles.
We have moles. Is moles equal to grams? No. So what do we have to do? We have to convert. Where do we define this conversion factor? Our periodic table. Okay, so we do 2 times, whoops, whatever our potassium is. I just need to show the work. 39.1 plus, what's the next one?
52.
2 times 52. And the next one was what, 7? 7 times 16. And what did that equal?
294.2.
And we put in at the top I already forgot the number, wow. 294.2 grams, 1 mole. What unit would we now have? Grams of potassium dichromate. We've got our answer. Okay. I'm going to assume that the other half of the class, if you did not start with milliliters, started with the molarity. Okay. So if we look at our units of the molarity, we've got moles of potassium chromate over liters of the solution. Which unit should show up on top? The moles, because that is the amount of our potassium dichromate, and my answer is an amount of potassium dichromate in the numerator. So I should put that mole value on top. So I have 0.150 moles of the potassium dichromate solution, and 1 liter of the solution. Are those units the same? Whoops. That's what we want. Grams of potassium dichromate. No, they're not. So we need to fix it. What unit did you attempt to fix? Okay. Said the mole value is not what I wanted, so we set up a conversion factor. And we're going to convert those moles to what? Grams of potassium dichromate. Why grams? That's what we want. Where do we find that conversion factor? Periodic table or the conversion that we just wrote out, the work for above. What unit do we now have? Grams per liter. Is that the answer? No. So I need to do what? I need to cancel out liters. Am I given any information that allows me to convert liters to anything in the question? There's nothing explicitly in the question. Can we convert liters to anything else? Yes. We could convert it to milliliters. Why would converting it to milliliters be useful? I am given milliliters in the question. So if I can convert the liters into milliliters, I now have a way to potentially go through and solve. How do I convert liters to milliliters?
Negative 3, sorry, just kidding.
10 to the negative third liters is 1 milliliter. What units do I now have? Grams per milliliter. What do I want? Grams. When do I want it? Sorry. Wow, that got... man, was the microphone not on for the rest of the semester? What the heck? Okay. So what unit needs to show up? I need milliliters, and I need it to show up top so that it cancels with that previous conversion. Okay. Am I given any information about milliliters? Yeah, I'm given 125.0 milliliters. Per what? 1. What unit? Nothing. Okay. Why? Well, when you look at the number given to you in the equation or the question, it says it's 125.0. If I put in any other number, it's not 125.0. If I put in any other unit, it's not milliliters. Punch it into the calculator, and I'll get the exact same answer. We may have changed everything around, but we did the exact same calculation. 125 is in the numerator. Yep. 10 to the minus 3 in the numerator. Yep. 294.2 in the numerator. Yep. 0.15 in the numerator. Yep. You can convert virtually any way you want to, and whichever pattern stands out to you as the easiest way to approach that question. Kind of makes sense? Okay. Questions? Anybody actually punch it into the calculator? Sorry.
5.5.
I heard a 5.556. 5.516. Did everybody get that? Grams of our potassium dichromate. Good. Okay. Yes.
Are we still doing sig figs?
Officially, yes, but since I didn't write down the number for sig figs, we're not going to worry about it. In that last one, let's see. Sig figs would need to be how many? 3, not because of the 125.0, but because of the 0.150, the molarity. Our molarity has only 3 sig figs. Based on answers that people have been sending me, or I've been helping people with on the practice exam, you should go back and review those rules. You do have explicit questions asked about sig figs. Okay? So you will need to make sure you remember those rules at least 5 minutes before the exam starts and 5 minutes after the exam starts, because you can answer those questions right away. Okay? So our application to molarity. A chemist needs to determine the concentration of a solution of nitric acid. She puts 745 milliliters of the acid into a flask with an indicator. She then slowly adds 0.2 molar of barium hydroxide to the flask until the solution changes color, indicating the equivalence point. She notes that 165 milliliters of barium hydroxide was needed to reach this point. What was the molarity of the nitric acid? Should sound vaguely familiar for everybody that has done the lab already, because this is what you did in lab. Okay. For all intents and purposes. Okay, so if we wanted to get really mean on this, we could turn it into a quiz. Was a reaction involved? Okay. If a reaction is involved in this, provide that balanced equation. What is the given information? Okay, so this is where setting up and just coming up with a way to pull information out of the question can come in handy. Once you've got that balanced equation, provide the given information about that species under the species in the equation. This can help you start to process where you're trying to go within the question. Okay? So let's spend a couple minutes working on that for our quiz. And by our quiz balanced equation, what did we react? HNO3. Good answer, sort of. Officially, we should be saying nitric acid, and then what we would write would be HNO3 plus, or aqueous, plus what? Barium hydroxide, which is Ba for the barium. OH is hydroxide, but that would be wrong. We need 2 hydroxides. Why? Balance the charges on them. That is also aqueous. This goes to be making barium nitrate. There's 2 nitrates to balance the charge again. Aqueous plus HOH liquid. You could also write it as H2O. I prefer the HOH to help show the type of reaction, or for balancing's sake. What type of reaction is this? It is officially a neutralization reaction. Okay. Double replacement is still technically true. It's one of those more right, less right situations. It is a double replacement reaction, but the better or more right answer is a neutralization reaction. If you got an acid and a base, it's neutralization. Okay. Before we move forward, what do we also have to make sure we've done? Balanced, which it is not yet. Where did it go? Oh, into water, right? And I think that's now balanced. The next part of the question, or the thing I asked, was to put the information you have about each of them underneath each of the species. So what do we know? We have 745 milliliters of the nitric acid. What else do we know? 165 what?
Milliliters of barium hydroxide.
You got 165 milliliters of the barium hydroxide. And we know the barium hydroxide is 0.200. And I would immediately shift to moles per liter. Okay, do we have any more information? I would argue no, but let's see if we can come up with one more piece of thing that we can put into this.
Changes color.
We'll address that in a little bit. What are you trying to get to? The molarity of the nitric acid. So we could go through and write right? So we now know what we're trying to solve for. So the way that I would go through and do this now, what I want as an answer, I need moles HNO3 per liters of HNO3. Do I know anything about either of those values? The moles or the liters? What do I know about? No? Let's try that again. Do I know anything about either of those values? A way to get to them relatively quickly and easily.
745 milliliters.
I have 745 milliliters of the nitric acid, and there I've got liters of nitric acid. Can I convert liters and milliliters? Yeah, so what I'm starting to do is put that in my head and say, oh, I can figure that out. Where should the milliliters show up in my conversion? Interesting. If I put it in the top, what's going to happen with my volume at the end of my answer? It'd show up in the top. My final answer, where did my volume need to show up? In the bottom. Roughly try and get a straight line on this. So I can do 745 milliliters on the bottom. What will go on top of it is 1, because I don't want a unit there and I don't want a number there to change the value of that 745. I know I need liters to be on the bottom, so I need to get rid of the milliliters and convert it to liters. What's the conversion factor between milliliters and liters? 10 to the negative 3 what?
Liters.
Liters is 1 milliliter. Okay. So if I look at my units, I now have the liters in the denominator, but I'm missing the moles of nitric acid on top. Now I got a bit of a problem. I need to somehow get moles of nitric acid, and if we look at my nitric acid column, I have no information, sort of, about the moles of nitric acid. Why sort of?
Do you know how many moles there is in the balanced equation?
From the balanced equation, I know 2 moles of nitric acid are required to react with 1 mole of our barium hydroxide. So I do know the moles of nitric acid. They are just related to the moles of the barium hydroxide. I think I'm going to run out of space with this conversion. What numbers need to show up in front of those? Okay, 1 and 2. 2 in front of? Why in front of the HNO3? Because it's in front of the HNO3 in the balanced equation. So I've now brought in moles of nitric acid. Cool, that is getting me closer to my answer. But at the same time, I've brought in this obnoxious unit of moles of barium hydroxide. Do I want moles of barium hydroxide in my answer? No, so that needs to show up in a conversion factor on top, so that it can cancel with the denominator. Do I have some conversion factor that gives me information about the moles of barium hydroxide? Okay, yes. What is that information? I can convert my moles of barium hydroxide using my molarity. But now what's my answer? This is going to get a bit tricky. It's moles per liter. Well, let's add a little bit more information. This first liter unit came from what?
Nitric acid.
It's the nitric acid. So really this is per liter of solution of nitric acid. That second liter is, are liters of solution of barium hydroxide. Okay. Well, what do I want for liters? HNO3. So that's in there, but now I got to get rid of this liters of solution of barium hydroxide. Okay. So I would expect liters to show up on top. Do I have a liters unit somewhere else for the barium hydroxide? I got 165 what? Milliliters. So I don't have a liter unit, so I'm going to need to convert that liter unit to milliliters. How do I convert the liter to milliliters? 10 to the negative 3 liters is 1 milliliter, and I am definitely out of space here. I'm now in milliliters of our barium hydroxide. Do I know a value for the milliliters of barium hydroxide? Yeah, that's my 165 over 1. Everything in the numerator, multiply. Everything in the denominator, multiply. Divide those two numbers, and we'd end up with our final answer. Questions about that? Is this the correct order for solving it? No. It all comes down to, in this case, what the class saw loudest as the next conversion factor. Okay. We do not have to run it in one line. We can run it in 2 lines. We can convert to moles, we can convert to liters, and then do those divisions. The hardest part within this question is realizing that that 745 milliliters belongs to nitric acid. That 165 milliliters belongs to barium hydroxide. Why does that become important? Well, do we put those values in different places? One case it showed up in the numerator, one case it showed up in the denominator. You have to make sure you put the number in the proper place. You put it in the wrong place, your whole answer goes to crap. Okay? Questions on that? Remember that limiting percent yield question that we showed a while back that had like 11 steps to it that you had to go through and solve? This is kind of that level of a question. When you move, if you move into 151, you will be doing this kind of calculation all the time. You're expected to crank through probably 4 or 5 of these in an exam. When it comes to your final, you're probably doing 1 of these type calculations, if that. Okay? Questions? I do not have the answer actually on there. Someone punch it into their calculator. What'd you get? 5.9, you said? And this would be moles per liter. This was our. And I'm going to estimate that in just a second. I'm not sure I can estimate that quickly. Actually, I think that's reasonable. Yeah. I think that does reasonably come out. Okay. As far as that estimation, it's a little bit weird because we have a mole conversion in there that messes with it. What I'm approximating is the concentration of barium hydroxide. Okay. I needed 165 milliliters. Okay. Barium hydroxide has 2 equivalents or 2 reaction abilities. Okay. So if I scale that 165 up to 745, they'd be the exact molarity. Or not the exact molarity, half of that, they'd be the exact molarity. Okay? I'm less than half of that by roughly a quarter, which drops me to roughly 0.1 molar. Okay? If you don't understand that, don't worry about it. Okay? Because effectively what I'm doing is doing all that conversion, or all those calculations in my head. Poorly. But that's what a guess is. Okay? Questions? Okay. So if we went through to do naming, we were responsible for recognizing the names for acids. Okay. When we go through and look at that last one ended up getting called or named according to its acid characteristic, and none of the others officially did. Why did we bother to go through and create a whole new naming system explicitly for acids? Okay, if you saw a container that said covalent molecule, ionic molecules, and acids, which one do you avoid sticking your hand in? Why do we invite a whole new nomenclature for acids? They're dangerous. Okay? We're triggering something in our kind of natural reflexes to say, don't touch that. Okay? And we get that kind of ingrained in our head. So that's why we end up naming things as acids. It ends up being a relatively reactive group of molecules. An equally reactive group of molecules are the bases. Acids react with bases. They are the polar opposites, if you will. So they will, when put together, cancel each other out if put in the proper systems. So if we look at where chemistry originally came from, it was just based on pure observation. So if some random person said, if I stick my hand in that, that hurts. Okay? I'm going to make sure other people know to not stick their hands in it because I don't want them to suffer. Okay? So they made some of these kind of observations. You'll notice that some of the other observations that came out of this are kind of fascinating. We've also got sour tasting. How did we come up with that observation? Someone had to taste our acid or our base. We have bitter tasting. How did they figure that out? Same deal. They went through and actually tasted your bases. Okay? And so when we look at, and then the next part is the feeling aspect to them. We found that some of these, or these sour tasting molecules, also had a sticky feeling. That sticky feeling being your hand melting. Okay? The bitter tasting ones had this slippery feeling. Interestingly enough, it's a slippery feeling because your hand is melting. Okay? But it's melting for a different reason, okay, or a different chemical reason. So when we go through and look at these, what we're really classifying or referencing in this case is that sticky feeling and that sour tasting all come from acids. What's the most sour thing you're aware of? That may be a dangerous question, but I'm going to try it.
Lemons.
Lemons, thank you, that works. Okay, and actually warheads, going after the same sour characteristic, citric acid. Citric what? Acid. It's the acid found in those species that's generating that sour taste. Okay, the bitter taste is typically due to soap. Anybody old enough or potentially young enough to have parents shove soap in their mouth to clean it out of all those bad words? Yeah, you might know bitter tasting. Okay, from having soap jammed in your mouth. What is soap? Soap is a basic compound. Okay. When we go through and react these, we end up forming a salt and water. Okay, so one of the things that we want to be able to do is to recognize what makes an acid and what makes a base without having to taste it or feel our hand melt off. Generally a good idea to avoid things like that. Okay? So that's where we come up with our definitions. A man by the name of Arrhenius was the first one to define our acids and bases. Okay? What he noticed is that when we took some species, and you add it to water, he was able to notice an increase in the concentration of hydrogen ions. Okay? Well, that hydrogen ion concentration is what is actually acting as an acid. So if we add something to water and we see or observe an increase in H+, we now have an acid. So that's our definition. If we think back to the naming of acids, how did you know it was an acid? How did we know this compound should be named as an acid? Aqueous, meaning we added it to water. Okay, why do we need to add it to water? Because our Arrhenius definition is when we add it to water. Okay, there's our first aspect. The next aspect, what else did we need to know that we had an acid? We needed a hydrogen. How did we know we were looking at an acidic compound? It wasn't just that it's aqueous, because if I write silver nitrate aqueous, that is not an acid. We need hydrogen. For you guys, the easiest way to determine if we have an acid is to look for the hydrogen in front. Okay, the hydrogen in front is our signifier for an acidic compound. Okay, this becomes particularly relevant when we look at a common anion. If we said sodium what? Acetate versus we have aqueous sodium acetate and we have acetic acid. How do we know to name that second one as acetic acid? We have the H in front. That is your signifier for an acid when you look at a formula. It is a horrible way to determine it, and it is very rarely ever used outside of this class. Okay, but what we're trying to do is give you some way to evaluate it relatively quickly. All right? So if you see a hydrogen in front, that tends to be a signal that you are looking at an acid. If we go through and look at a base, it's the same general concept. We take sodium hydroxide, or we take our basic compound. When we add it to water, we see an increase in the concentration of hydroxide ions. Okay. So if I add a species and hydroxide shows up, hey, there's a base. So one easy way to decide if you have a basic compound, do you see hydroxide in the formula? It's about as simple as that. Our acid compounds are a little bit more complex because if we look at the acetate ion, hydrogen does show up in it, but those are not acidic hydrogens. We can't count those. Why? Take organic chemistry. Okay. So when we're looking at these, we're trying to come up with as simple approximations as possible. And the fun thing about these definitions is that while we talk about them a lot, and we spend a lot of time emphasizing them, they're ultimately pretty useless. Okay? They are way too narrow of a definition to actually apply to anything useful within chemistry. Okay? So while responsible for knowing them, that's about the extent of it. What we'll move into starting on Thursday is our more useful definitions and potentially even our really, really useful definition that's way too broad. We'll look at some applications of acids and bases, looking at reactions, conjugates, naming things. We'll throw in a little bit of equilibrium, and then we'll probably stop there on Thursday. And we probably won't get into gases. We'll save that for next week.